Okay, next is line integrals in conservative vector fields. So this is a concept that allows us to use a very simple formula, and that formula is going to be f of b minus f of a to compute a line integral. You don't even need to know the equation of the line, we just need to know the start and stop points, that is a and b. So the intuition is because moving in conservative vector fields, such as like a gravitational field, to use a real life physical example, provides the same total work done no matter what path is taken. So if you go from the Earth's surface to 30,000 feet directly, or if you go from the Earth's surface way up into space and then back down to 30,000 feet, it doesn't matter because you did negative work coming back down that just cancels out the extra work you did. So mathematically, the idea here is called the FTLI, or the fundamental theorem of line integrals. The advantages of this is obviously this simple formula as mentioned above, which means we don't have to parameterize the function in terms of t, etc. Also, there is less integration needed usually. So there's two things we have to do to use this method. First, we have to actually know or prove that it's a conservative vector field, and the test for that is that the curl of the field is 0. And as a reminder of what the curl is the del operator crossed with the vector field. And just on a little bit of a tangent here, divergence, because you usually learn that when you learn curl, divergence is the del operator dotted with the vector field. But anyways, if the curl of the vector field is 0, it's conservative, and you can do this. So the second thing that you have to do, which is a bit more involved, is you have to find what's called the so-called potential function. So it's called the potential function of the vector field function. So here's how this goes. What you're going to do is assume that the vector field given in the problem, which we're going to call big F, is the gradient of some potential function. So to do this, we're going to take the antiderivative of the vector field. And we're assuming that the I hat component of the vector field is the partial with respect to x of the potential field, which we call little f. And the j hat component of the vector field is again the partial of f with respect to y, etc. So we integrate one of them, and say we integrate the I hat component, which is p, with respect to x. And instead of adding a plus c on the end, we add a function g of y.